So we've looked at the process of writing a Taylor polynomial where we need to find these coefficients, but we want to find these coefficients in a faster way. So let's look at kind of an in general version of this. The other thing that we want is we want these functions to match as closely as possible. So what we're going to be doing is we're going to look at our polynomial function in general and trying to figure out what these coefficients might be in general. So the first thing that we want is a polynomial equation p sub n of x. We're going to look at one that is centered at c. So we have a sub 0 plus a sub 1 x minus c plus a2 x minus c squared plus a3 x minus c cubed, and we want to go on until we get to a sub n x minus c to the n. So because we're looking at something centered at c, what we want to look at is p sub n of c. So we want to look at c being the number we plug in. And the reason why is when we do that, we get, instead of x minus c, we get c minus c. C minus c is 0, so any term where we have x minus c is now going to go to 0. So I'm just plugging in c. In doing so, all of those terms that had an x minus c are going to go to 0, so we're left with a sub 0, or a sub naught. Because we want them to be as close as possible, we want p sub n of c to equal whatever our function is at c. Because of that, we know that p sub n of c is the same thing as a sub 0. And a sub 0 then has to equal f of c. So we know our first coefficient is going to be the y value of f of whatever our function is. So now that we've found that one, we're going to look at the first derivative. So we want p prime. So we need our derivative first. So I'm going to do the derivative. This is all of x. So I'm going to have a sub 1 first plus, this was squared, so I'm going to have 2 a sub 2 of x minus c. We're going to have 3 x minus c squared. I'm going to write the fourth one on here just because. So we'd have 4, I forgot a term. So it's 3 times a sub 3. And we have 4 times a sub 4, because those are the coefficients we're looking for. X minus c cubed, and then that's true for everything up to n. So we have n times a sub n times x minus c, and then it's to the n minus 1 because we've taken 1 away. So what we're going to do now is we're going to plug in c just like we did before. So anywhere I have an x, I'm going to have a c instead. Otherwise, it is the exact same thing as what we just wrote. And because we have c minus c a bunch of times, those are all going to go to zeros again. So we get a sub 1. Because we want p prime of c to equal f prime of c, because we want those derivatives to match up. Each kind of point in time we want it to match up. P prime n of c is a sub 1. So we know a sub 1 is going to equal f prime of c. So the derivative at our point. Okay, now we look at the second derivative. So p double prime n of x. We take the derivative. A sub 1 is a constant, so now we're looking at 2 a sub 2 times x, but that goes away, plus. Here is where I am going to write it out very specifically because we're looking for a pattern. So the next term would be 3 a sub 3 times x minus c squared. So we're going to take 3, we're going to multiply it by the 2 because of power rule, and we're still multiplying that by a sub 3. And then we have x minus c to the first power. We have 4 here, so we're going to have 4 times, its exponent right now is 3, so we're going to do 4 times 3 times a sub 4 x minus c squared. And that's true all the way down to a sub n, so we have n times n minus 1, because that's our new exponent, times a sub n times x minus c. We take 1 more away, so instead of minus 1, we're going to do n minus 2. And just like every other time, we're going to plug in c. So we want our center value to be plugged in so we can kind of get rid of some things. So we have 2 a sub 2 plus. Everything is the same except c instead of x. So we have c minus c, so this term is going to go away. This term is going to go away. And this term is going to go away. So all of this goes away, and we are left with 2 a sub 2. We're still looking at those derivatives to be equal to each other. So because we want p double prime n of c to equal f double prime of c, we know 2 a sub 2 is going to equal f double prime of c. The thing is, though, is we want our coefficient to be by itself. So we want a sub 2 to be by itself. So we're going to take this, and we're going to say a sub 2 is equal to f double prime of c divided by 2. Okay, so we want to look at another one. So p triple prime of n. So derivative, so 2a sub 2 is going to be gone, so we have 3 times 2 times a sub 3. X minus c goes away, so we just have 3 times 2 times a sub 3 plus. We have 4 times 3 already, times, okay, we do power rule, so 2 times all of this, times a sub 4, and we still have an x minus c because we take 1 away from our exponent. And that's going to continue on until we get to n. So we have n times n minus 1. Our old exponent was n minus 2, so that's going to be multiplied here. Times a sub n, x minus c, and then we have n minus 3. If we plug in c for everything like we've been doing, we have everything is exactly the same, except instead of x, we have c. Once again, anywhere we have x minus c, we now have c minus c, so it is going to go away because it's going to equal 0. So instead of x, we're going to have c. So we have a bunch of c minus c, so they go away. We have them no more. So we have 3 times 2 times a sub 3. Okay, so when we look at this one, we know that p triple prime of n of c is 3 times 2 times a sub 3. There's another way that we could write that. So if we kind of look at what's going on, we have 3 times 2, we have 4 times 3 times 2, we have n times n times 1, n minus 1 times n minus 2. And if I wanted to, I could multiply all these by 1 and it wouldn't change anything. So what that means is that I could rewrite this as 3 factorial a sub 3. And because we want this to equal our derivative, so because p triple prime n of c, we want it to equal f triple prime of c, we're going to say that 3 factorial a sub 3 is equal to f triple prime of c. We also want that coefficient to be by itself, so we're going to kind of change that along to say a sub 3 is equal to f triple prime of c divided by 3 factorial. Well, when we look at this, if I were to do this again, we'll have 4 times 3 times 2 times 1 realistically, so this is going to be 4 factorial here. So we have 4 factorial times a sub 4. So we're going to have something like the fourth derivative at our point C divided by 4 factorial is equal to our coefficient. So this is going to be something that we use because we're going to be seeing this pattern. So what this tells us is when we have a function, our coefficients are going to look like a sub n is equal to f, the derivative of the nth derivative of f of c divided by n factorial. So the pattern we start to see is, so instead of having to figure out what these coefficients are every single time, we can kind of use this instead. So if I need to do a fourth degree Taylor polynomial, I don't need to go and find all of these different things unless I have to. So we're going to change our formula just a little bit. So our formula is now going to look like Pn of x equals, instead of a sub 0, we're now going to use f of c. So whatever our function is, we're going to use that center, plus our first derivative at our center times x minus c, plus our second derivative at our center, but we're going to divide that by 2 factorial. And I'm only doing the factorial here because our factorial matters in all the other ones. And we're multiplying this by x minus c squared. And we can even do a third one. So f triple prime of c divided by 3 factorial times x minus c cubed. And this is going to be true all the way up to our nth term. So f, the nth derivative of f evaluated at c divided by n factorial times x minus c to the nth power. So we're still going to be having those x minus r center. We're used to a power every time. The only difference now is we can kind of zone in on what we want with those coefficients.